Hi guys, welcome to today's recording. I will be going through NCEA Level 2 Chemistry's 2.6 examination, Chemical Reactivity. So let's get into it. Now the thing with this particular topic is that 30% of it is just NCEA Level 1 stuff, which is a rates reaction. So I'll probably go through those a little bit quicker than I normally would, just because it's lots of writing and most of it's level 1 concepts, so it shouldn't be too hard. Okay, so let's have a look at this particular reaction. We can see that we have a reaction here, and as you can see, the mass of the reaction, the mixture decreases over time, and it decreases rapidly at the beginning, but decreases less at the end. Same level 1 stuff. Okay, so why does the mixture decrease in mass? Because you're losing your CO2, so you're losing CO2 gas. That's why you decreasing in mass. And explain the changes in rate reaction between as the reaction proceeds. So again, very straightforward. Just at the beginning of the reaction, you have lots of chemical reactants that haven't reacted, readily available to collide, so they collide more often, high effective occlusions per unit time, therefore high rates of reaction. And as the reaction takes place, you have less chemicals available, therefore lower number of occlusion per unit time. Okay, so very year 11 stuff. Okay, so at the beginning you have high frequency of effective occlusion because you have more particles, and then the CO2 leaves, so the mass decreases rapidly at meaning it's a higher rate of reaction. At the end, there are fewer reactants left, so there's a decrease in the frequency. So just be very careful with the word frequency. Frequency is equivalent to per unit time. Okay, so if you use frequency, don't say per unit time anymore. Or if you say the number of occlusion, you can reword this, like say the number of effective occlusion per unit time decreases. That's perfectly fine as well. So they're replaceable. Okay, so it's level 1 concept. We level 2 chem students, we should be able to do this quite comfortably. Next one, so this is chips, this is powder, so the surface area is going to be the one that we're interested in. Same concentration. Okay, so refer to the occlusion theory. Okay, so when you have powder, just remember powder have higher surface area. When you have higher surface area, you got more particles exposed, readily available to collide, and therefore they're immediately available, they can collide. You have a higher frequency of successful collision, or a higher number of successful collision per second or per minute, per unit time, whatever it is. Okay, but at the end, because your concentrations are the same, you have the same amount of calcium carbonate, you will produce the same amount of carbon dioxide gas. So that means the end product will be the same, but just one happens a lot quicker. Okay, so here we go. So calcium carbonate powder, larger surface area, so more particles are made readily available, exposed, immediately available, whatever you want to say, and then more effective occlusion per unit time, faster rates of reaction. The other one, not take longer, fewer particles, the opposite. So they will eventually produce the same amount of mass because you have the same amount of reactant. Okay, so if I gave this to an NCEA Level 1 student, they should be able to do this as well. Okay, so if you look at this, H2O2, so this is elephant toothpaste, a very cool reaction. So the Ki is a catalyst, because what it does, it lowers, that's spelled horribly wrong, catalyst. So what this does is that the changes refer to the activation. Okay, so what it does is that if you have, is this an exothermic reaction? This is an exothermic reaction. Because you don't know this is, it doesn't say, but I know this is an exothermic reaction. I'm just going to draw this diagram to show you. So what does a catalyst do? It lowers the activation energy, so more reactant particles will collide with sufficient amount of energy. Okay, very simple stuff. This is probably the only year 12 new content that's new here. So it provides an alternate pathway with lower activation energy. So when the particles collide, a higher proportion of these will have sufficient amount of energy to overcome the new lowered activation energies. Therefore, you have a higher frequency of successful occlusion. Like, to me personally, I feel these questions are like just 3 points, and if you can't, and there'll be if you didn't even do that well from NCEA Level 1, like this is like 4 ticks, 4 points at least, A4 from this question. And if you're someone pushing for merit and excellence, you cannot afford to lose these, because these are like guaranteed free merit and excellence questions. Because you learned this last year, word to word, nothing really new here other than the activation energy stuff and the catalyst. So there's absolutely no excuse not doing well for this. But then some students tend to get complacent. They're like, I did this last year, I got excellence in it, then didn't practice, turn up the exam, miss out the didn't write the full details, and you miss out on the excellence or merit. Okay, now question 2. So this is where equilibrium comes in. So this is level 2 stuff. Okay, so this is going backwards. KC is the products and reactants ratio. So the thing on top is the products, the thing on bottom, so this is my reactants, this is my products. So my equilibrium will look like this: 2NO plus O2 equilibrium turning into 2NO2 gas. Okay, so just remember the squared is the coefficient at the beginning. So for the reaction above, the Kc is 230 at 44 or 6.44 times by using the Kc expression. So where did that? So I'm just gonna borrow that number here. So we got what is it? Kc equals NO2 squared, I think it was, squared, and then divided by NO squared times oxygen. Okay, so these are the numbers that we got from the the thing above. So they're just trying to ask you to show, all right, use the concentration above. So what you need to do, just substitute the numbers in. And this is not difficult, guys. Just substitute numbers in, and then get the answer. So it's right here. So 734,000. So if you look at the Kc value, the Kc value is this number. So 644,000. So 644,000. So if this system was at equilibrium, these two numbers should be exactly the same, and they're not. Therefore, it's not at equilibrium. Okay. Now, to reach equilibrium, would the forward or backwards reaction need to be favored? Okay, so we need to come back here. So we have a higher Kc, all right? So our Kc in this particular case is higher than what it should be. So Kc is a ratio of products divided by reactants. So what we want to do, so to reach equilibrium, we need to lower the Kc. How do we lower the Kc? That means we need to have less products and more reactants. That means we need to shift to the back, favor the forward, the backwards reaction. Okay, so here we go. So Kc is higher. Kc is to decrease the value of Kc because we want the value to go down. The concentration need to increase, of the reactants need to increase, or the products need to decrease. So we shift to the reverse reaction. All right, nice and simple. Next one. So this is at equilibrium. So what happens when you add a small concentration of CH3COH? So if we add a small amount of this, Le Chatelier's principle states that in order, when you do this particular change, you want to minimize the change. So if you increase the concentration of CH3COH, they want to shift to the right to use up some of the added CH3COH that you have added in. So as a result, the concentration of the H2O would decrease. The concentration of these things on the right hand side would increase because you're shifting to the right hand side. Okay, so as this concentration increases, the system is no longer equilibrium. It will minimize it by favoring the forward reaction, producing lots of products. Now if we add dilute sodium hydroxide, okay, so let's look at this equation again. Oops. If we add dilute sodium hydroxide, where the hell is my thing? Okay, so let's get rid of these lines. So what are we doing now is that we are adding sodium hydroxide, adding NaOH. So what's going to happen to the NaOH? The NaOH is a base, right? So this base will neutralize this. Because sodium hydroxide has OH minus, so the OH minus will neutralize the base, the acid. So what's going to happen? The H3O plus concentration will decrease, and then the system's like, hey, we're losing H3O plus, we need to make more. So again, you shift to the right to make more H3O plus ions. Okay, so here we are. So the NaOH reacts with H3O plus, so removing it, so we need to favor the full reaction to make more of it. Okay. Next one, when the temperature increased, Kc increases. Okay. So again, sorry, I need to go back to this equilibrium. Okay, so what we got? Do we have an enthalpy number here? Nope. So when the temperature, so it's this equilibrium, so CH3COOH plus H3O plus, just a dissociation of this CH3CO minus. This is just from the previous part. I just can't be bothered going back and forth. Okay, so what are we doing? We're increasing temperature, Kc increases. Okay, so you need to break this down into two parts. When temperature increases, that means two things. Oh well, just one thing. We need to favor the endothermic reaction. Endothermic reaction is favored. Why is that? Because we need to absorb the added heat energy. Okay. Now, when Kc is also increased, so remember, Kc is a product and reactants ratio. If this number mathematically increase, that means they have more products, less reactants. And how would that work? How would I get more products and less reactant? That means we favored the forward reaction. Okay, so the forward reaction we favored. Now we know increased temperature, we favor endothermic reaction. Boom, favored endothermic reaction is a forward reaction. Done. Okay, so you just need to break it down to two parts. So temperature increases favor endo to absorb the energy. Kc increases, that means we got more products, so that means we're favoring the products. So that means adding, so therefore increasing heat favoring the full reaction. So therefore the full reaction is endothermic. Very nice and easy. Okay. Once you get your head around this endothermic, exothermic stuff, it's going to be a walk in the park. All right, so we're going to go through question 3 now. So this is looking at the acid-base section. So H3O minus acting as an acid. So what it means is going to give it the H away. So it's going to be CO3 2 minus because it lost an H plus. And the H plus went over here. So that's why it's H3O plus. As a base, that means it's going to accept an H plus. So it's H2CO3 plus OH minus. Okay. So a solution of nitric acid has a concentration, calculate the pH. So this is just H3O plus concentration. You just go pH equals negative log, and then this concentration and this concentration is exactly the same. So you just literally negative log 0.0625, and that's going to be, give my calculator, this is going to be 1.20. Okay, and calculate the hydroxide ion concentration if it has a pH. Okay, so this is very easy again. So we want the OH minus concentration. There are two ways of doing it. You can just go 10 to the power negative pH to get to 3.16 times 10 to the power negative 10. This is your H3O plus concentration. So and then you can just use Kw, well, not a square bracket. You can just use Kw divided by the H3O plus concentration. So it's 1 times 10 to the power negative 14. Divided by 3.16 times 10 to the power negative 10. That will give you 3.16 times 10 to the power negative 5. Another method that you can do is this, by just simply using pH 14 minus POH, which give you 4.5, and then you need to understand that OH minus is just 10 to the power negative POH. If your teacher never taught this, then don't use this method. Okay, either one works. I have, this one doesn't really, doesn't matter which one you use. Okay, for part C, the table shows the concentration of the two solutions. Justify which have the same, so they have the same concentration but different pH. So you just need to understand this is a strong base. Okay, so you can show the equation for all of these. What this does is that completely dissociate. So you have a lot of the OH minus ions. That's why the pH is really high. And then this guy and this guy, they're weak. So this is a weak acid. This is a weak base. You can tell by the by the pH. So the weak acid means that when this partially dissociates in water, you are only going to produce a very small amount of H3O plus. So this concentration is very small, due to the partial dissociation. And then the other one is a weak base. So what is it going to do? It's going to accept H plus ions from here, and it's going to go there. So because this concentration is very low, you are going to have a pH that's higher than 7, but not that much higher. Okay, so pH, there you go, is a reflection on the H3O plus ions. The higher the pH, the lower the H3O plus. So this guy is a strong base, completely dissociate, so you have a lot of this, high pH. Weak base, partially dissociate, low OH minus, therefore the pH is about 7. Whereas the other one, the pH is less than 7 because it's a weak acid and they will partially dissociate. Okay, and I think the last question, so elaborate on the electrical conductivity. Why are these good, poor, good? So again, equation guys, you just go HCl completely dissociates in water, completely dissociate, you will have a high concentration of the free moving ions. NH3 is a crappy conductor because it will partially dissociate, so you will only have a very slow concentration of the free moving ions due to the partial dissociation. And then your NH4Cl is the hardest one because first thing first, you need to dissolve this into, this is a salt, you need to dissolve them first, and then you can tell that your NH4 plus can further dissociate into the NH3 and H3O plus. So why is this a good conductor of electricity? Because you got lots of ions from here, which will conduct electricity really, really well. Okay, so for anything to conduct electricity, free charge particles, which means you need ions. HCl strong acid, so good conductor because it completely dissociate and ionize. All right here. And whereas the ammonia is a weak base, partially dissociate, very little concentration of ions, and that's it. Okay, so hopefully this is helpful. You know, leave a like and subscribe if you haven't, and share the videos with other chemistry students that are currently struggling, and I'll see you guys next time. Bye bye.